Hi guys, this video we will talk about vertical coordinating dimension. So modular floor plane for vertical dimensions. In order to apply the modular coordinations, we need to define a reference plane. So reference plane is called the modular floor plane for vertical coordinating dimensions. In nation standard, the modular floor plane is defined such a way as to be continuous all over each story of a building. So regardless of the fact that the level of the upper surface of floor covering may vary within each story. So the reference planes remain the same across the height. So in vertical planning approaches, MV, the modules is equal to M, which is 100 mm. So floors are placed within a modular floor zone of n times m increments, and floor to floor heights are vertically placed and n times m increments. So example here, so the floor to floor height is n3 times m, and your slab, your floor is within the boundary of n2 times m, and the floor to ceiling height is n1 times m. So this is the vertical controlling dimensions as explained in the Malaysian standard 1064. This is a change in floor height, as you can see, floor to floor level, and this is called floor zone, where it comprises the floor, your floor structure, and may include finishing. And this is a floor to ceiling height, which is this is your floor, the distance is up to your ceiling height, and this is floor to floor height, where the first floor finishes top surface of first floor until the top surface of the second floor. So as you can see here, these are all in modular dimensions. So there are two vertical controlling dimensions. Number one is the main controlling dimensions, and number two is the intermediate controlling dimensions. So the main controlling dimensions are the roof zone and the floor zone, and the floor to ceiling height and then story height. And then between these controlling dimensions are the intermediate controlling dimensions, which window head height, window sill height, and door head height. So what needs to be emphasized here is that the the setting, the definition of a reference plane. So the three positions of the modular floor plane defined as a reference plane for the vertical modular dimensions in building design is shown in this figure 16. So in slab, you have upper surface of floor covering, and you also have upper surface of rough floor, and then you have the upper surface of structure floor. So these are the three surfaces. So the plane and floor will not totally coincide due to unevenness of floor surfaces, joints, and tolerance. So the vertical modular dimension should be taken from modular floor plane. So illustrations of vertical dimensioning are shown in figure 17, 18, and 19. So this figure 17, you can see here the reference plane, the modular floor plane is positioned at the rough floor, as you can see here. The grid line is coincide with the rough floor, not on the surface of the structure surface C or B, but it is coincide with A, with the floor covering, not rough floor covering, level A. So this is one example. You can set the modular reference plane to be on the floor covering. So throughout the entire building, so the grid line will be on the floor covering on level A. So floor covering, which is level A. You can also put it on B or C on the rough floor, or like example in this one on the rough floor. So the communication throughout the assembler, or architect. So a clear communication will be established. So your grid line will be on you need to define your grid line module floor plane to be to coincide with which level, either it is a covering, rough floor, or directly on the structure. For example, in this example, so anything in between can be in modular dimensions to fit in the modular size of the grid lines. So this is the coinciding with the upper surface. This is your upper surface. So the grid line is coinciding with the upper surface. So the next floor will be also on the upper surface covering. So this is on rough. This one is on structural. So by establishing it, by defining it, you can get a clear communication between all the party involved in constructing this building. So this is another example. In summary, you have a horizontal and vertical dimension, vertical coordination. So you need to coordinate your vertical dimension and then horizontal dimension, which nation standard has provided its preferred sizes. So it can be referred to, and then I think mostly all the industrial player, or the people involved, be it designer or constructor or even manufacturer, they are all well versed in this preferred sizes, so it'll be easier for you to communicate or for your design to be well versed by them. So in example here, you can see the vertical coordination is n times 3m here, from this grid line to this grid line. And then you have your vertical coordination n times m. So this is your floor, and this is your I think shear wall. This is your external wall. So external facade is placed flush and outside of the modular line. As you can see here, this is how they design it. Flush outside, and as you can see here, the structure, the cross wall is placed within technical zone or space T1 as in alternative 2. So your cross wall is non-modular, but it's placed between modular zone. So this one will be modular zone, this one will be modular zone. And floor slab is placed within the modular zone of n times m. Internal partition wall is placed flush on either side of the modular line. So it is placed flush. So that is all on section 2 and 3 of nation standard. Next section is joints. The standard talks about joints. So fundamental principles for design of joints in buildings. So this section, if you go through the standards, we'll discuss the three main headings: the geometrical, the sizes, and then the structural elements, and then the environmental element of the joints. And then it is necessary to distinguish between joints between components, and then the joints between parts of one component. So, for example, you have window and another window. So there is a joints between components, or windows and window frame, or window frame and wall. But the joints between parts of the component is like a component of window or component of door. So some parts have like a collapsible or sliding door. They have parts, and there are joints between the parts. So while general conventions will be directly applicable only to the joints between components, some aspects may also be relevant to joints between the parts of component. So generally we talk about joints between components because there is interfacing. You need to fit your window between the walls, for example. So generally we talk about that, but less on parts between components, because the components come from the manufacturer, and as long as the parts, the components are in modular dimension, it will be easily fitted in the modular sizing or modular zone. So there are three basic principles of joints, as I mentioned earlier. So the first one, let's take a look at the first one, geometrical, the jointing products in relation to joint profiles. So the position of joint profiles of the components in relation to the common joint reference planes, and the joint clearance based on the specified positions of the joint component, and expressed as its maximum and minimum value to accommodate deviations. Deviations may occur from the manufacturing, during setting out, and then during your placing, action, and then during the functioning of the components. For example, if you open up Windows, so you need the like uh, deviation, it's like tolerance, allowance. Its size, the joint's clearance also need to be expressed in size, in relation to the work size. So the work size, which is different to the component size. Work size of the components with a view to standard conventions for dimensional coordination. So the clearance should also allow, for example, we talk about this. The clearance should allow for joints, or for joints between the components. And then the second part, the second principle of joints is structural properties of joints. So joints shall be designed for all dynamic and static conditions. So whether the component is being used, dynamic, or the components are placed, static conditions, deriving from joint situation within the building for the life of the components in the building. So basically, the durability uh, of the joints. And then environmental properties of joints. Joints shall be designed to provide performance such that the assembly by the components achieves required overall performance. It can be assembled. In many cases, this implies a suitable continuity of the specific performance of the joint components during the life of these components, the building, taking into account maintenance. So you need to also consider, when designing joints, you need to also consider the lifespan of joints. So it is more durable and reliable throughout its lifespan. So components and finishes, building parts are perceived as components. So building process is assembling of the components. So building parts is the component itself. Building process when you assemble the components. So there are two influencing factors: the position and sizes of a component, where it is placed externally, internally, exposed to weather, extreme condition, and then also the tolerances. The Lorentz allowed between them and their coordinating spaces. This will influence the components, how you're sizing the components, size of components. Designing with components must be conceptualized early in design stage, bearing on choice of planning grids and approaches. So when you are designing or selecting your components, it is in early design stage. You select it, and it also depends on your grid lining. So if you choose, like for example, increments of 3m, so best to place components that suits 3m. So there are three components, type of components: structural components, columns, beams, floor slab, walls, staircases, and then non-structural components: cladding, partition, doors, windows, and then finishes: ceiling finishes, floor finishes, wall finishes. So the modular rules for 3D components, as you can see here, these are all the 3D components, 3D model dimensioning of components. Components are dimensioned and placed inside and within the horizontal and vertical planning module. So you need to place it within the modular spaces. So for non-monolithic 3D components, components are dimensioned within the horizontal and vertical planning modular increments. And the load-bearing and self-bearing parts, if any, are on the outside of modular plane. So if it is non-monolithic, it can be placed. So it need to be placed within, but the load bearing and self bearings are placed outside. As you can see here, the load bearing is placed on the outside of the grid module compared to this one that is placed the within the grid line. These are all the basics guidance on when you are designing components that comply with the modular coordination. So you have two, non-monolithic and monolithic. For columns, basic dimension is 3M. Dimensions fit into modular grid, and dimensions are for finished dimensions. It is advised to based on finished dimensions. And for beam, the increment is M. Floor zones with false ceiling, beams accommodate in the floor zone. So as we talk about vertical coordination, beams should be in the floor zone. So you have a hanging false ceiling, so false ceiling can be within the floor zone, but your beam must be in the floor zone. Beams that only affect surfaces, not walls and partition below. So the beams that only affect the surfaces running through the wiring or the running on the ceiling. For the floor zone without false ceiling, distance between base of beam and floor slab must be modular. So if the bottom grid line here is flush with your beam, structure beam, so the distance between your base of beam to the floor slab uh, should be modular to accommodate the components between this, the uh, intermediate zone, the floor height, the window height, the sill height, and so on. Depth in submodular increments of 0.5 m or 0.25 m. So for floor slabs, so the increment will be 0.5 to 0.25 m, depends on your thickness. So it's like running from 250 mm to 500 mm. A precast slab fit into structure grid of 12 m, the width, not the thickness. Floor zone, I need to highlight here the space allocated for floor assembly. This is floor zone. When you look at in your horizontal coordination, this is floor zone. The modular zone is between these two grid lines, so all the floors are within the floor zone of modular dimension, and extends from reference plane of ceiling to the finished floor surface above it. So the reference plane is from the ceiling to the finished floor surface above it. That is floor zone, as we talked uh, uh, as we talked before. So your ceiling to the top floor is your floor zone. Ceiling accommodated within the floor zone composition may vary. You can include, not include, depends on your type of ceiling. Top of floor zone is equal to top of floor finishes. So ensure that your top floor zone is coincide with the top finishes surface. The base of floor zone is the bottom of ceiling or floor below. So for precast floor slabs, width is a multiples of n times 3m, n times 6m, 12m, depends. But these are all the multiplications. So the width, you can, if it is, you have a 30-meter slab, so 10 times 3m, or is it, uh, or whichever that fits, 30 meter, 60 meter, or 30 meter, 5 times 6m, depends on your precast slab width. It can be a multiplication of that. You can easily assemble on site with less wet work. So we've talked about this before. So this is your non-modular section, and this is your modular section. So this is our modular section. You can have either like this, or you can have interaction like this. This is modular. This is modular. And the precast walls. For walls, precast load-bearing walls Length of walls determined by the planning grid, your horizontal control, and dimensions, finish wall dimensions. So it'll be your finishes surface here. Talked about this before. External should flush on the inside finishes. Then example here is positioned within the boundary. In cases wall do not fill the whole wall zone, where structure allows, wall should be lined with one side of the zone to minimize number of detection pieces. So if the wall is too thin, it can flush on one side only, not flush on both sides. So that on one side you'll be fully fitted, but on the side maybe there'll be a slight adaptation you need to cut and fill of the wall. But that is a way to minimize. Doors, dimensions for door sets given in the mission standard. Controlling spaces be preferred dimensions to allow the doors to be fitted without under adjustment. So basically, if you modular dimensions, your door is modular, uh, it can fit without any adaptation, without any cutting or adjusting. For window, dimensions for window sets are the whole set of frames. Sill reference planes may coincide with floor reference plane. So it can be your top, your sill reference plane is the same as your floor reference plane. Your sill, for example, here your window sill is here, coincide, but it can be not coincide, depends on your window height. So window head reference plane may coincide with ceiling reference plane, but the width is important. Stairs, length of flights and landing dimensions are modular. So when this is the length of flight, it should be modular. For example, n times 3m. For example, this is 2 times 3m. So this is 2 times 3, 1 3m. This is another 1 3m. So it is modular so that it can be fitted within your intermediary reference zone. So stairs located in between floor coordinating line. So the stairs is located horizontally within the coordinating line and also horizontally within the horizontal coordinating line. So top of stairs coincide with the top of floor zone. So this is how you manage it. So your beam also flush with this floor zone, and then your staircase also flush with the top floor zone. So these are all the guidance given by the mission standards. So that everyone in the designing, the structural engineer, the architect are clear that where your staircase ended, where your beam should be flushed, and so on, so that uh, it helps in coordinating and placing all the other components within the uh, building. So there will be less adaptation. That is our main concern. So this one, all example you can look through. So how they place a single flight, do double flight stairs. So how they are placed within the modular coordinating lines. And lift course, for lift course, the guidance is external dimension should be modular, the outer wall flush with the grid lines. If it is more than one lift, whole assembly is treated as single element. So you have 4, so you need to arrange the lift core in modular assembly, single element of modular, but can be put into several grid lines. This is another example. As you can see here, a floor plan. The outer wall is flush on the inside, and the party wall, the line should is the wall should be inside. So as you can see, it's an increment of 3m, 3m, 9 times 3m, 9 times 3m. So it's increment of 3m. So you can work around with your room sizes, be it bedroom, dining room. You can work, but in the multiplication of 3m. So if it is 2700 meters, mm, so it is a multiplication of 3m. You can have your room with a width of 6,000, 6,600, and so on. Same goes within here. So the components selected here, the door sets should also be with 3m. increment. For example, 600 mm, which is 2 times 3 m of width. This is a vertical coordinating dimension, as you can see here. The first floor, floor to floor height here is in modular coordinating dimensions. The ground floor is 18 times 2m, 14 times 2n on the first floor, second, third, up until the roof floor. As you can see, the column also in modular coordination. Again, this is a floor zone, just to highlight the example. This is floor zone. As you can see here, your top surface slab coincide with the floor zone grid line, and the beam, the structural beam is within the floor zone area, which is 6m. Then you have your sill height, window head height, and then this is sill height. This is example of Sembawang, typical plan apartment. You can see with this, it is in modular coordinating dimensions, which is 3m. The wall is 3m, and then you have a dimension here for windows, I think, for sliding door. And the service balcony is 18m, which is a multiplication of 3m, 6 times 3m, and then this 6m for wall, for I think for wall zone here. But as you can see here, there is a non-modular dimension here beside the 3m. So you can also put adjust like that. So I think the modular coordination is uh, in this section only. The modular section of 3m, but otherwise others are also in modular, but not in 3m multiplication. So your 3m can be positioned within this zone, but this is some adjustment, 13.5m. This is adjustment, so that's how you get your total measurement is 119.5m. So overall, it is just a planning. So for example, you want to place your door set, window, wall panel. If it is in 3m's, for example here, this is 3m, so it can be adjusted to be fully fitted between these three. For example, if you have a 3m slab, it can be placed 6 numbers here in 18m. But in here, you need to have some adjustment adaptation. And that will be all. Just a reminder to do your uh, assignment for uh, attendance, and then I think it'd be helpful for you to have some picture of how the exam question gonna be. So basically, the exam question is more like this: you need to design your floor plan layout for horizontal coordination, for horizontal coordinating. So you need to design your floor plan layout. Uh, I give you the dimensions of the component, for example, the column, the slab. So you need to adjust your floor dimensions. I'll be giving you a minimum sizes. You can go large, but be mindful that you need to be in modular coordinating lines, and also uh, 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 also you can adjust. For example, in the Sembawang, it'll be helpful for you to look all this example given to you in the slide. And that will be all. Thank you for your attention, and good luck in your exam.